Hello and welcome back. In this video, we are going to look at transfer learning or retraining an image classifier. And what I mean by that is if if you're let's say if you're trying to do image classification task, and for that instead of building a model from scratch, what we can do is take pre-built models that have already learned several features and use that as a starting point to build our classifier. And there is a resource for that, and that is called as TensorFlow Hub. If you go to this site, TensorFlow Hub, on this side, both for tf1, that's TensorFlow older version, and the new version tf2, there are several models that have already been created by people, and we can download them and use them in the different types of tasks that we have. And so for this particular exercise, what we are going to do is we are going to use a model which is the efficient net version 2 from the TensorFlow Hub. And again, the code that we'll be going through in this particular video is can be found on this side, which is the TensorFlow docs. I'll be simply copying the code from that side and trying to explain what the code is doing as we go through it. And here I've already copy pasted some of the lines that we need, and one of them is this particular model that we are going to use. And if you go in here and if you search for that model, so let's say if I copy this and put that here, and let's say if we search for this model, we will get a hit for that. And this is the model. There are two of this type that we have, and if you click on the model, then it will open a web page where you'll have the information about the model. So the model that we are going to use is this one, feature vector. I think this is the same that we just opened. No, it's different one. So here what we have is we have the name of the model, which is the efficient net v2, and here is the performance for that efficient net v2 based on training efficiency, parameter efficiency, then additional information here, and plus furthermore comparison. We can also use the models that are on TensorFlow Hub directly with minimal lines of code, and that is written here with or without optimization. And if we need to, we can always open this entire code in Google Colab and test run it there, or we can download it. So that's a large file, 744 megabytes, and we can use that as a starting point for the classification model that we are about to build. So what we are going to get started with, as usual, we'll do the setup. And for setup, we need to import a couple of libraries. So let's do that. Setup, and here we'll import iter tools. Then we'll import OS, and then we have import matplotlib.pylab as plt, import numpy as np, then we'll import TensorFlow, import TensorFlow as tf, import TensorFlow Hub, TensorFlow underscore hub as hub, and then we'll print the version. So print tf version, and here we have tf dot underscore underscore version underscore underscore. That's the TensorFlow version. Likewise, we'll print the hub version, print hub hub version, and here we have hub dot underscore underscore version underscore underscore, and then finally we'll look at the GPU. And before we do that, while thinking about that, let's change the runtime so that we can use the GPU, sorry, not manage sessions. What I'm going to do is change the runtime type and change this to a GPU and say save. And this will, by the time it restarts, we should have this line of code written done typing. So we'll go ahead with the typing. GPU is, and delete previous runtime, say yes. Is GPU is, comma, then we have the available, and then if tf.config.list underscore physical underscore devices, and here we say GPU, else not available. So this is what we have, and when we run this line of code, we should see that we do have a GPU. So GPU is available. That's the version of the hub, and that's the TensorFlow version. We are at 2.9.2. And in the docs, the version that is used is, I think, 2.11.0, but this should work as well. Now, the next thing we need to do is select the model from the TensorFlow Hub, and we'll see which one. We'll use the one that we just saw above. Select the tf2 saved model module to use, and in here we'll specify the model name, and the model name that we'll specify is this one. So I'm going to copy this string right there and paste it here. Model underscore name is equal to this, and then we'll also we'll create a dictionary model underscore handle underscore map is equal to, and here what we'll have is the name of the model, which will be the key, and associated value with that key is going to be this URL for that model from which it can be downloaded. So that's that, and that's the dictionary we have created. With this done, and if you look in the docs, there are several other models that are available, and you could try all of those or some of those and see how that affects your accuracy score. And finally, we'll select the image size. The image underscore size underscore map is equal to, again, this is going to be a dictionary, and here as well for the dictionary we have the same name of the model, and the value here for this particular model, the image size is 512. So with that setup, we can now begin the next part of the code. So the next thing we'll do is we'll use the model, we'll create a model handle. So model underscore handle is equal to model underscore handle underscore map dot get model underscore name pixels is equal to model underscore image underscore size underscore map dot get model underscore name comma 224. And now we can print selected model, and here we specify the model underscore name, and then we can specify the handle. So model underscore handle, and that's the closing curly braces there. And so when we look at, wondering why it is not highlighted. Okay, so when we run this, we see that this is the selected model, and that's the URL from which we are going to get the model. And we'll fix the image size. Image underscore size in caps is equal to pixels comma pixels, and that's the pixels we have above. So if you run the pixels, we see that it's the 512 that we specified. Again, we can print f colon input size image underscore size close parenthesis, and that's what we have as input size. And finally, we need the batch size, so we'll put the batch underscore size is equal to 16. Okay. So with that, now we can get our Flash dataset that we have. We have been working with flowers in past 2-3 videos, so this again is another Flash dataset. Set up the flowers dataset, and for this, to get the file, we'll use the Keras utility and put the images in this folder. In this variable, we'll put them in a folder, and that can be read by this variable. Data underscore dir is equal to tf.keras.utils.get underscore file, and I'll go ahead and open the root folder where that particular file should appear, and should appear in here inside of Keras, and when we run the file, we should see it there. File, and then here we have flower underscore photos, that's the first one, and then comma, we specify the URL https colon / storage.googleapis.com / download.tensorflow.org comma / example underscore images flower underscore photo flower underscore photos dot tgz, and then we put a comma, and down here we will say untar is equal to true, and when we run this, we should see on the left, we should see the new files appear, the folder appear. If it doesn't, then we'll have to refresh this. So let's refresh this, these folders, and now we can see it. We have the datasets folder, and inside of the datasets, we see the flower photos.r.gz, and we have the flower photos folder with 1, 2, 3, 4, same 5 flower types that would be our classes. Next, what we'll do is we'll build our dataset, and let's create a heading here, set up flowers, and now we'll build the dataset. So we have build dataset, and here what we did is we wrote the same line of code again and again. So this time we'll create a function def build, or let's start out with what we had done. What we have done previously. We said tf.keras.preprocessing image underscore dataset underscore from underscore directory, and in here we specified the data, the path, that's the name of the directory, and then we have the validation validation underscore split split is equal to 0.20, then subset is equal to the subset that will specify. Earlier we used to say either it was training or it was validation, and then label underscore mode is equal to categorical in this case. And then we need to provide the seed. Seed is equal to 1 to 3. Image underscore size is equal to image underscore size, and then we have batch underscore size is equal to 1. We are specifying batch size as 1 here. Now what we did in the previous case is we would put validation split. Okay, we would put train underscore ds here, and then add the name of the folder here. But what we'll do in now is, instead of doing this, we will put all of this code inside of a function. So we'll say def build underscore dataset that takes in a string, let's call that subset, and colon, and because we are in a function we need to put a tab here, and that subset is going to replace this string here, subset, and we are going to return this particular this entire block. Okay, so that's how we have created the function, and let's run the function. Now we can use the same function to build our data set. Train underscore ds is equal to build underscore data set training, and then we have so that when we run this we should be able to get the train underscore ds. Then class underscore names is equal to tuple train underscore ds dot class underscore names, and then we have train underscore size is equal to train underscore ds dot cardinality open close parenthesis dot numpy open close parenthesis, and then train underscore ds is equal to train underscore ds dot unbatch dot batch, and here we have batch underscore size, and finally train underscore ds is equal to train underscore ds dot repeat. And when we run this, hopefully, okay, so this is working. Now we have created a train dataset with 2936 files for the training purpose. And now there is an optional part that we can do, or we can kind of skip that, which is normalizing, preprocessing, and augmentation of the images. In this case, we'll write the code for both. So let's do that. Normalization underscore layer is equal to tf.keras.layers.Rescaling, and here we have 1 point divided by 255. That's the normalization layer. And next what we'll do is create a preprocessing model. So let's run this first. Let's run that. So that is done. Next we have preprocessing underscore model is equal to tf.keras.Sequential, and here we'll use the normalization layer, normalization underscore layer, and that's our preprocessing model we have created. And the reason why we have set this up like this is we'll now add the data augmentation parts to this preprocessing model. Okay. And for this particular training purpose, we can say do data augmentation is equal to true or false, but for now we'll set this to false. And if this were true, then we would do the following steps. If do underscore data underscore augmentation, then preprocessing underscore model dot add, and here we'll specify tf.keras.layers.RandomRotation, and we'll specify the number 40. So that's one layer that we are adding. The next layer we can add is preprocessing underscore model dot add. The next layer we can add is for translation, tf.keras.layers.RandomTranslation, and here we will specify the values of 0, 0.2, and then we have preprocessing underscore model dot add, and here we will specify tf.keras tf.layers.RandomTranslation, and with a different set of values 0.2 comma 0. Okay. So with this done, so if this were set to true, then these three layers would get added to the pre-processing model. Additionally, we can say pre-processing underscore model dot add tf.keras.layers.RandomZoom, and we'll specify a value of 0.2 comma 0.2, and following this we'll add another layer, pre-processing underscore model dot add tf.keras.layers.RandomFlip, mode is equal to horizontal. Yep. So these are the different layers we are adding to the pre-processing model, and we can use the augmentation part if we set this false to true. Now with all this all in place, let's run this, and now we look at then we can apply this pre-processing to our trained data set. So let's say apply the pre-processing to train underscore ds. So train underscore ds is equal to train underscore ds dot map lambda images labels, and then we have inside of this parenthesis a pre-processing underscore model, input is images, and then comma the labels along with it. Okay, so with this we have now built we have now pre-processed labels. There's a typo there. Okay, so that's the train data set we have. Likewise, we can work on the validation data set, and for this we have validation underscore data set is equal to build underscore data set, and we have validation and build, miss the D there. Okay, data set validation, and then validation underscore size is equal to val underscore ds dot cardinality open close parenthesis dot numpy, and then we have validation underscore ds is equal to validation underscore ds dot unbatch dot batch, and here we specify the batch underscore size. Next we have validation underscore ds is equal to, we'll map the pre-processing, normalization, not the entire pre-processing, validation underscore ds dot map lambda images comma labels colon, and here we'll specify the normalization underscore layer, and the input will be images and comma labels. So that's our validation data set. And as you can see, earlier we had 2936 for training. We have the remaining 734 for the validation. With this setup, now we can define our model, and let's go in here and define the model. Defining the model, and for this we can set there are two options. One is we can use the previously trained model from the TensorFlow Hub as is, or we can do some fine tuning. For now, what we are going to set is we set the fine tuning to false. So we'll create a variable do fine underscore tuning is equal to false, and we'll build the model now. Print building model with model underscore handle, and that's going to be the model handle that we had created above, which is that particular model. And now we'll create a sequential model in Keras. Model is equal to tf.keras.Sequential, open close parenthesis, open close square brackets. And here we'll say tf.keras.layers.input layer, and here we have input underscore shape is equal to image underscore size plus 3 comma, and the second thing we need is we are going to use the model pre-trained model from the TensorFlow Hub, and that can be written inside of the sequential model in Keras like so, where hub.keras.layers.input layer, sorry, my mistake, hub.keras.layer, then open parenthesis model underscore handle comma trainable is equal to do underscore fine underscore tuning, which we have already set to false, so there won't be any fine tuning going on. We just have a hub.keras underscore layer and the model handle there, comma, then we have the final two layers. Last time we used the dropout layer to improve our validation accuracy, and we'll do the same here. Layers dot dropout, and we'll set the rate to 0.2, and finally we need the dense layer, tf.keras.layers.dense, and here we have length class underscore names. So because those many are the classes we need to look at, and kernel underscore regularizer is equal to tf.keras.regularizer s dot L2, and we'll set the value to 0.1231, and this is the model we have now. So below this, once we'll run that particular cell, so building a model, and once that is done, we'll wait for this to finish, and let's go into the root and see if there are any additional files we start seeing inside of the Keras folder. And yep, I don't see anything new that has come up. So while that is running, we'll write the next line of code, model.build, and here we'll specify none comma plus image underscore size plus 3 comma, and then closing parenthesis, and then we look at the model underscore summary, and this should give us model underscore summary. Model is not defined, wondering why that is the case. Model build, this is none image size plus that model dot summary. Oh, my mistake, it should be dot summary and not underscore summary. Okay, so that's the model we have. We have the Keras layer here, then we have the dropout layer, and then we have the final dense layer. With the model now ready, we can compile and train. So let's do that. So here we have, let's create a heading called training the model, and here we'll compile it, model.compile optimizer is equal to tf.keras.optimizers.sgd, and we'll specify learning underscore rate is equal to 0.125 comma momentum is equal to 0.9. Then we have loss is equal to tf.keras.losses categorical cross entropy and entropy e lowercase from underscore logits is equal to true, label underscore smoothing is equal to 0.1, and we need the matrix, and we'll set the matrix to accuracy, and that's we'll compile the model compilation is done. Now we'll fit the model. So steps, we'll specify the steps per epoch. Steps per epoch is equal to train underscore size, and then we have validation underscore steps is equal to valid underscore size, and then history is equal to model.fit, and here we can specify train underscore ds, epochs is equal to 5, then steps per epoch is equal to steps per epoch that we have specified above. Validation underscore data is equal to val underscore ds. Validation underscore steps is equal to validation underscore steps, and then here we can say dot history. Okay, so not there, my mistake. We already have a parenthesis down here, so I'm going to put the down history there. So with this, then we now let's change this to hist. Okay, so we have the commas in place. Wondering why we have a red squiggly line there. Run this, and there's a mismatched parenthesis. All right, so that's because of that. And this will run through 5 epochs, and because we have a GPU, this should run really fast. And after that, we should be able to plot the validation accuracy, validation loss, along with the values for the train data set. And let's look at the resources, and we can see we have a 15 GB of GPU RAM available, so that's plenty. And we have 12 gigabytes of RAM, and then plenty of almost 100 gigabytes of disk space. It's a powerful combination we have for the practice session that we are going through. And as you can see, it has immediately used 8 gigabytes of GPU RAM. So if you're wondering what specs I need if you're trying to buy a GPU, I'd say the GPU needs to have a minimum of 16 GB of RAM if we are trying to do some sort of deep learning on it. I mean, lower RAM would also work, but I think minimum 16 should be what would help kind of run through faster iterations while learning. Okay, so looks like this is going to take a while. What I'm going to do now is stop the video here and come back when the entire training is done. Welcome back. So what I've done, I've stopped that training because it was going to take an hour for just one epoch, and there are 5 epochs, so it would have taken 5 hours just to run through this training. Instead, what we are going to do now is do some changes, and here we'll use batch size, and then comment that out, and again use a batch size here and comment that out, and let's try and run this again and see how this would work. And as you can see, this is much faster. And at least for this uh, video purposes, this should be fine. Okay, I'm going to close out that window, and here we can see that the accuracy is 0.94. Let's look through the second epoch when it comes through, and this is still taking a while, but much faster than what we had in the previous run. So let's do this. I'll again stop this video, come back when this run is done, and hopefully it won't be a long time from now. Yep. So let's stop this. Welcome back. Here the run is done, and it took around 3 minutes 28 seconds for this to run. And let's look at the scores. We have the validation accuracy, that is 0.91, and the train accuracy is 0.96, and that's a good number to start out with, given that we are using the pre-trained model in our model. Now let's plot these results. So using the history, plt.figure let's do that, and then here we have plt.figure, plt.y label, loss, training, and validation. And the next thing we need is, let's put this parenthesis inside of this and one outside. Then we have plt.x label, and here we have training steps. Then plt.y limit, let's set it to 0, 2 and comma 2. And then we have plt.plot hist, that's the history, we are plotting the loss, and plt.plot hist, and here we have the validation loss, and that's one figure we have. And then the second figure, we need a T there. Second figure, I'm going to copy this entire thing, put it here, and we'll change the heading here. This is going to be accuracy for training and validation, and again the y lim will change it to 0 to 1, and this is going to be accuracy, and this is going to be validation accuracy. And when we run this, we should see two plots. Here, as you can see, the loss, the validation loss and the training loss are pretty much similar. And again, if you look at the accuracy for training is little bit higher, but if we change the y-axis limits to say 0.5, we may be able to see some, we get a close-up. It is slightly higher, but still the validation accuracy is pretty close to the training accuracy. And that's without doing any augmentation. So if you run this model again by setting this to true and setting the augmentation to true, the accuracy may go up further. Now what we'll do next is we'll try to print some of the values from the validation set and try to predict the values. So here we have x comma y, so let's put another heading, and let's say predict, and now we have x comma y is equal to next iter val underscore ds. So we are getting an image from there. Image is equal to x square bracket 0 comma colon and colon, and we are getting all the rows, columns, and channels from that image and creating this new array image here. true underscore index is equal to np dot argmax y, and we are getting the value of y at the index location 0. plt dot plt dot im show, and this is going to contain the I think this will have the label. So if we run this, y is not defined because we haven't defined that yet. But let's run this and we'll come back to that line. Image, and then we have plt dot axis. I will switch the axis off, and plt dot show, and we should see an image. So that's the image we have, and if we have run this, that's the index. Okay, we just get the index there, and this is the image of flower. We can now use uh, this value for prediction. So prediction uh, prediction underscore scores is equal to model.predict np.expand underscore dims image comma axis is equal to 0. Okay, and then predicted underscore index is equal to np.argmax prediction underscore scores, and then we can print the values. Print true label, and here we have plus class underscore names true underscore index. So that's the index for the class name. Print predicted label, and here we have class underscore names and predicted underscore index. And when we run this, we should see the output with the true label, and so the true label is sunflower and the predicted label is also sunflowers. So that's how what we did was we used a pre-trained model from TensorFlow Hub and use it to build our classifier using Keras. And the final thing that we can do is, actually there are two more things. The first is we can save our model, and so to do that, let's create a heading save model. We can say saved underscore model underscore path is equal to, we'll save this to temp backslash tmp backslash saved underscore flowers underscore model underscore, and we'll specify the model underscore name here in curly braces, and tf.saved underscore model dot save model comma saved model path. And if we go in this directory, let's find temp, which is this one, and inside of temp we should see that model appear after we run this cell. Right now there's no model, nothing that says saved underscore flowers underscore model. So when we run this, after the run is done, we should see the file. Until then, I'll just keep talking. We still do not have. There's a tf.hub.modules. Wonder what that is. Okay, so this is going to take a while because I'm guessing the size of that particular saved model would be around 700 megabytes, because that was the file size that we downloaded from TensorFlow Hub. And here we see the timeline for the cell. It is past 47 seconds and still running. Let's look at the resources. We have the resources. It is using the GPU. and using 7 gigabytes of RAM. So definitely we need, you have a computer for deep learning purposes, definitely needs to have more than that RAM. And okay, so it's so that warning, unfound untraced functions as restored body functions. Warning. Okay, so the model has been saved, and I'm trying to figure out where that is. Let's refresh this, and oh, we still do not see the model in here. Saved model. Okay, here it is. Saved underscore flowers underscore model, and if we click on that, those are the files associated with it. And awesome. So that model we have created. The next thing is what we have done in the previous video as well is look to see how this would work in TensorFlow Lite. And so let's look at that. And the docs do have a code for this. So why don't we go through this? Because anyways, after the end goal would be to deploy it. And if you are trying to deploy it in TensorFlow, this would be handy. Deployment to TensorFlow Lite. So I've been looking at why the code was crashing, and it was because of I was running out of RAM, and so I won't be able to run this part of the code. I tried changing the image size all the way down to, we scroll back up here. I've tried to change it down all the way to 32, but still running out of memory, that is RAM. But still, I'll go through the code, but won't be able to show you the output of the code after it is converted to TensorFlow Lite and how it compares with the original TensorFlow. So here we are defining the variables. Again, optimized light model, we're setting it to false. Number of calibration examples, we're setting it to 60. And do we need a representative data set while the optimization? This is a default set to none. And here is a definition sort of what representative data set is. And here we are creating a lambda function for that. And down here then what we are doing is we are converting the saved model from the original TensorFlow model. And then here is the if block for optimization, and this is actually where the conversion takes place, and that's the line of code where the runtime crashes and it goes out of RAM. So all 12 gigabytes that is allocated gets used suddenly and code will crash. So after that, we just have this. We write to the new TensorFlow Lite model file, and then here we can use that to using the tf.lite.Interpreter, and then this is the function that uh, that is the light underscore model name for it. It will allocate tensor, get the input details, set the tensor size, invoke the interpreter, and get the output details to return the output tensor. And finally, this is the evaluation data set that is created, and then we have this set of for loop that will run through the evaluation data set and calculate the probabilities for the class probabilities for the light model and the TensorFlow model. And eventually this line of code just shows of how they compare, how the TensorFlow Lite model compares with the original TensorFlow model. So that was it for this video. I hope you enjoyed learning in this video as well. And the issue of RAM, I'm still not sure if will be upgrading. So this is the option now. If I upgrade it to Colab Pro, this gives 32 gigabytes of RAM, I think. If it is available, and if that's the case, then maybe this rest of the code will run. But at the moment, I'll end this particular video here, and hope to see you all in the next video. Until then, if you have any comments or suggestions, please do let me know in the comment section below. Please like, share, and subscribe. Thank you.